Hello and welcome to the Further Maths Support Programme revision recordings for A-level modules. Today we're looking at Edexcel Mechanics 2 and this is the third part of those recordings looking at work, energy and power. If you're interested in any of the other topics for Mechanics 2, these are also available on the site where you found this one. Taking a look then at an excerpt from the Edexcel specification for Mechanics 2, this is the work, energy and power section. You need to be aware of kinetic energy and potential energy. You need to have the concepts of work and power sorted out. You need to know about the work energy principle, this is absolutely crucial, and the conservation of mechanical energy. And you're going to be working on problems involving motion with constant resistance and sometimes up and down inclined planes. And that's the example that we're going to be taking a look at shortly. So first of all, main concepts. You need to be aware that work done, change in energy, and force times distance moved are all different ways of explaining the same thing. You need to know the formula for kinetic energy and for gravitational potential energy. And you need to be aware of the concept of the work energy principle, which I state like this: input energy in a system is equal to output energy in a system. That means that any initial kinetic energy or gravitational potential energy plus any work done to increase the energy of a system. So for example, if an engine is working to pull something along in a system, that's increasing the energy of the system. It's converting fuel into additional energy in the system. And the sum of those is equal to the final kinetic or gravitational potential energy in the system plus any work that's been done to reduce the total energy of the system. So for example, if work's been done against friction, that's energy that will have left the system, and therefore we include that in the output energy side of the calculation. You also need to know that power is rate of work being done. It's the same as energy per time, and it's the same as driving force multiplied by velocity. It's very important here that we consider the idea of driving force, not resultant force in a system. So the driving force or tractive force is the force that's being provided by the system which is producing the power, the system that's doing the work. So what force is being provided by the engine or by the person pedalling the cycle, etc. Not the resultant force on the system. Those are generally two different things. Okay, so let's take a look at an example. If you're playing along at home and would like to stop the recording at this point and work the question through, I invite you to do so. I'll be working through the solution here on the screen, so as soon as you restart the recording, you'll be able to see the solution. Okay, so we have a car on a slope. Its mass is 750 kilograms, so its weight 750 g. We have this constant resistance to motion of R. Down the slope and up the slope, the engine is working at 15 kilowatts, and that's producing a tractive force which I'm going to call T. It's going at a constant speed of 20 meters per second, so I'm going to say then that its acceleration is 0, and that's important because it means if it's going at constant speed that the forces parallel to the slope are balancing, because there's no resultant force, therefore no resultant acceleration. Before we get into using the forces though, we're going to take a look at the power equals tractive force times velocity calculation. Just notice here that power has to be given in the standard units of watts. In the question here it's given in kilowatts, so we need to convert that into watts. So 15,000 watts is equal to our tractive force that we're going to find here multiplied by velocity, which is 20, and that gives me a tractive force then of 750 newtons up the slope. Once I know that, I can then consider the forces parallel to the slope. I know that because there's zero acceleration, that those forces balance, so I know that T up the slope must be completely balanced by R and the component of the weight, 750 g sine alpha, theta, which I haven't put on my diagram, down the slope. That means that R, which I'm looking for, is going to be 750 minus 750 g over 15, because sine theta is 1 over 15, and if I pop that into my calculator, that gives me the 260 newtons that I was hoping for. Let's go ahead to part 2. Again, if you want to pause at this point and work through the question yourself, you're very welcome to do so. So the system has changed a little. we still have this same car moving up the slope. Just going to resketch that as quickly as I can. Oops, 750 G down the slope. We still have our force R, which is 260 newtons down the slope. We have a new power, 18 kilowatts up the slope, and that's going to produce a different tractive force, which I'm going to call T1. Again, it's moving at 20 meters per second, but this time, because we've increased the power, it's going to have a larger acceleration up the slope. And we can calculate that again using power equals tractive force times velocity. That's going to mean 18,000 equals T1, my new tractive force, multiplied by 20. So my new tractive force is going to be 900 newtons. This time when I work parallel to the slope, I can't balance the forces. I'm going to need to use Newton's second law. Up the slope, my forward force is my 900 Newton tractive force. That's resisted by 260 newtons down the slope, and also by the component of the weight, 750 G sine alpha, which I know is going to be 750 G over 15. That's my resultant force in the upward direction, up the slope direction, and that's going to be equal to mass times acceleration according to Newton's second law. And again, popping that into a calculator gives you acceleration is 0.2 meters per second squared. Just a little tip there, accelerations like this are generally fairly small, so if you end up with a value for the acceleration that's larger than 10, there's a good chance that there might be a mistake in your calculation, so do go back and just have a quick double check to make sure all your numbers are correct. Let's take a little look at example 2 here. Again, if you want to play along at home, please do pause the recording at this point. We have an object which has a mass of 0.5 kilograms, so its weight 0.5 G downwards, and also it's got this resistance to the motion, which they're calling R, in the upward direction. If we use the work energy principle here, we can say that the initial kinetic energy of the object, because that's all it's got at the start, that's going to be equal to the final gravitational potential energy, because the kinetic has all gone, plus, remember we put here work done against friction, so work done versus R, our resistance to motion. Okay, so that's our work energy principle, input energy equals output energy here. So initial kinetic energy, half m times 20 squared. That's equal to the mass times g times the height it rises through, plus, and work done against friction is work as force times distance moved, so r times 10, and again a little pop that into your calculator, and we come out with resistance to motion must be 5.1 newtons in here. Okay, I hope you found that useful. When you have a moment, I strongly suggest going to the Further Maths Support Programme home website and just have a look at the other support that we can offer to schools and colleges and to students working with further maths, and I wish you all the best with your examinations. Thank you for your time.